Chapter 17, Lesson 4. In the previous lesson we talked about titrations, and we talked about titrations of strong acids and bases. Here we'll talk about the same except in regard to weak acids and bases. So unlike the strong, whenever you titrate a weak acid, the conjugate base is formed from a weak acid. So when you have a conjugate base, he will affect the pH of the solution. And so when all the acid, the weak acid, is neutralized, you will have a bunch of conjugate base left over. Now a conjugate base is basic, and so the pH at the equivalence point will be higher than 7. Recall that in the case of strong, the pH was 7 because all you had is water left over, but in this case you have a conjugate and water. So very often phenolphthalein is good to use in this case because phenolphthalein can actually measure the pH a little above the equivalence point, or I'm sorry, a little above the neutral point of 7. This is, if we think of this as 7, phenolphthalein can do roughly above 7, so you can use it for weak acids. Phenolphthalein is actually here. Phenolphthalein is pink in base and clear in acid. This is the famous indicator. So here is the pH curve of a weak acid. Now it differs slightly from the strong acid that we've seen before. Notice it's still an S-style curve with the equivalence point right in the middle. However, you'll notice that the overall curve is slightly shifted up. And you'll begin at a higher pH because you have a weak acid instead of a strong acid. And your equivalence point, notice, will be, again, not at 7, not at the neutral point, but higher. In this case, roughly 8.2 or 8.3, and maybe more like 8.5 actually. And so the curve is shifted up, and in this case we will have to consider more than just what's left over. So here's how we will do the calculations. Firstly, we will find out how many moles of strong base is added to the weak acid, and this is how many moles of the weak acid will be converted to its conjugate base. Because remember, now when we neutralize, we have this conjugate base that shows up. We will have I have to calculate how many moles of the weak acid we have left over, and because before you get to the equivalence point, we're going to calculate this portion, because we will still have some acid and its conjugate base. Recall that an acid plus a conjugate base gives you a buffer. So we will actually have a buffer to deal with. We have talked about buffers in the first two lectures. So for the buffer, we'll have to use the Henderson-Hasselbalch equation to solve for the pH of the buffer. So let's try how this looks with a problem. The problem says calculate the pH of the solution formed when 45 milliliters of your base, again we have a strong base, is added to, in this case, 50 milliliters of 0.1 molar weak acid. This is good old acetic acid. A weak acid whose Ka from the back of the book is 1.8 times 10 to the negative 5th. So what we'll have to do is let's go ahead and find out how many moles of base we have and how many moles of acid we have. So let's do moles of base, which is in this case hydroxide. We'll multiply liters by molarity as we've done before. We have 0.045 liters. And we have ourselves 0.100 molar solution. So again, it's like dividing by 10. You end up with 0.0450 moles of base. We'll do the same thing to the acid. Let's find out how many moles, in this case, of acetic acid, HC2H3O2. This is our weak acid. So we have 0.050 liters times 0.100 molarity, and we get 0.0050 moles of acid. So these are the two amounts that we are going to put up against each other. Now you'll notice that all the base will neutralize all the acid. So we will have, very similar as we had in the previous case, a little bit of acid left over. In fact, we'll have left over, we can subtract the two, and we'll have still left over the 00050 moles of acid. However, we'll also have a bunch of base left over, and because of that, we'll have to set up the buffer equation. So on the next page, let's go ahead and, since we're dealing with the weak acid, let's go ahead and include and have our modified icebox, if you recall. So we have our acid, acetic acid, and along with its conjugate base, which is C2H3O2 minus plus H plus. And again, remember the Ka of this acid was 1.8 E negative 5. So let's remember our modified icebox was the beginning, change, and ending. So what we began with was 0.0050 moles of our weak acid. This is the amount that we just calculated. Because we're dealing with a weak acid, we have to think about it in terms of equilibrium. And we will say that here we don't begin with much of the conjugate base. We have a tiny amount, but not too much. So we can kind of ignore that, because what we'll need to look at is how much we have left over. Remember, this is not necessarily an equilibrium icebox. This is the beginning, change, ending to the icebox. Now, as we add the strong base, as we add this much strong base, all the strong base will neutralize our weak acid. So we will subtract from here 0.0045 moles, because we're losing all that because of the neutralization. But anytime we move from here, we will have to add 0.0045 moles here. And then we're not going to care too much about the H plus. That is going to be given to us by the HH equation, by the buffer equation. So let's not worry about H plus. Remember, we're doing the buffer equation to solve for what's left at the end. So what we'll have here is we'll have left over 0.0050 moles of my acid and 0.0045 moles of my conjugate base. And these really are the same amounts that we have here. This is our moles of acid left. And now let's go ahead and use the buffer equation. Because we have ourselves both a weak acid and its conjugate base, we have ourselves a buffer. So for the buffer, we will have to do pH is negative log of Ka plus base over acid. And these are usually in brackets. But remember, we can use moles as well as molarity. So let's plug this in. Our negative log of Ka, our Ka is 1.8 E negative 5. So negative log of 1.8 E negative 5 plus our base, our conjugate base is 0.0045. Our acid is 0.0050. And go ahead and plug these in. I would suggest plug these in separately. We forgot a term here. It's plus the log. This should have a log. I'm sorry. We have a log here from the buffer equation. You have to log that value. So go ahead and calculate that. And we get ourselves 9 here. I'm sorry, if you log that, we should get ourselves 0.954. Double check, make sure you got the same answer. And then take the negative log of 1.8 E negative 5. You should get yourself 4.74. Add these two together. and your pH comes out to be 5.69 or 7.0. This is our pH. Notice the pH is still acidic, and that's because we have not neutralized all of our acid. Because remember, in the pH curve, before we get to the equivalence point, we have to go through the acidic range. So we're probably about here. We're still in the acidic range, but we are climbing up to the equivalence point, pH. So this was a calculation of a weak acid and a strong base. On the next example, we'll do the opposite. We'll actually do a strong acid versus a weak base. But before we do that, here it says, with weaker acids, the initial pH is higher, which makes sense. Notice if you have a weaker acid, these are the Kas. An acid that's weaker has a smaller and smaller Ka, which means its pH begins higher and higher, and the changes near the equivalence point are less distinct. So for something like we just did, the equivalence point pH, you can still see the vertical range. But for something like Ka of 10 to the negative 8, notice how indistinct and it's your equivalence point range is, and it's really tough, or much tougher, to find where it becomes vertical. And that's really what you're doing. In fact, in the future we will be able to produce these types of graphs, and just from the graph itself you can find the equivalence point, the vertical portion you're going to be looking for to find the equivalence point. But here's our strong acid. The strong acid begins all the way down here, and then the weaker you are, the higher up you go, and the less distinct your equivalence point is, as a general idea. So why don't we do the opposite now? Now we're going to titrate a weak base with a strong acid. In other words, in the flask down here, or in the beaker, now we have a base. This is our unknown. And in the burette, we have an acid, and this is our known. Now, the titration curve, notice, is flipped. So we have, you can say, the reverse S or the Z curve. Previously you had the S curve, now you have the Z curve. Just like your beloved instructor, his first name is Sergey, his last name is Zinovchik. So both of these actually have been created specifically to be able to, for me to teach you. That way they coincide. So what you'll begin with, because you have a base in here, you'll begin at a high pH, and then as you titrate, you'll still get your equivalence range as you decrease, and then you'll end up at a low pH, because after all the base is done, you have with you some acid. Now, the same thing happens if you have a weak base. The second curve is actually for a weak base. This one here is for a strong base. In other words, if you're titrating a strong base, if in your flask you have a strong base. If you have a weak base, you begin at a lower pH, which makes sense. Weak bases have lower pHs, and then your equivalence range is also less distinct, or shorter. But you can still find, and we're still looking for this equivalence point, the point at which all the acid and all the base have been neutralized. And customarily, methyl red is a good indicator to use for this, if you have a weak base. Looks like we need to record something here. So the pH at the equivalence point, this is important, is less than 7, because you begin with a weak base, and when a weak base is titrated, you end up with a conjugate acid. And that conjugate acid at the equivalence point is what rules the pH. So notice we're below 7. So we're going to go ahead and do a problem. We're going to finish this lesson up with a problem, a titration problem of a weak base. Notice we have 40 mils of our 0.100 molar NH3. This is our famous weak base. We have the pH of this, or I'm sorry, the Kb of this is 1.8 times 10 to the negative. Take a look at your -5, just like the acetic acid. So we'll have to find out how many moles we have, and then we'll have to find out how many moles we'll have of the acid. Now, actually, here we're asking for the pH at the equivalence point. So we will be neutralizing all of our base. So you can say all of base is neutralized. Because all the base will be neutralized, what we'll have left over is conjugate acid. Conjugate acid will rule the pH at the equivalence point. So this is a good thing to remember before we get into this titration. Again, we're trying to hit the equivalence point exactly. Here is what we're trying to hit. And let's go ahead and find out how many moles of base we have. Moles of NH3. It looks like we have our liters times molarity will be 0.040 liters times 0.100. We end up with 0.0040 moles of NH3. Now remember, at the equivalence point, moles of acid equals moles of base, which means we will have to say that we have that many moles of a conjugate base. Remember, all of NH3 actually converts into its conjugate, and the conjugate of NH3, when NH3 being a base gains a proton, becomes NH4+. So we actually have the same amount of NH4+. We have 0.0040 moles of NH4+ at the equivalence point. All our base became conjugate acid. So remember, this is at equivalence point. These are equal. Moles of base are equal to moles of acid. What we'll need to do now is find the molarity of our weak acid that's left over and use the icebox on him. Now we don't have a buffer here. All we have, so you can put down no buffer, all we have here is just the weak acid that we'll have to contend with. So let's go to the next page. So we had, let's recount, we had 0.0040 moles of NH4+ at equivalence point. Now, before we can find out the icebox, let's go ahead and we're going to put this into the icebox. We can go ahead and put him in right away and then find the pH at the end. So NH4+ is what's ruling the solution now. So we have to contend with him. Let's go and write out the equation here. NH4+, as it acts like an acid because it's a weak acid. Let's write out its weak acid equation, and it breaks down back into the NH3 and H+. The Ka of this will have to be found out from the Kb of NH3. Now remember, Ka is 1.0 times 10 to the negative 14 over Kb, which in this case is 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. So our Ka of our acid, whoops, go ahead and divide those two. We can find out what the Ka of the acid is. .56 e negative 10 times 10 to the negative 10th. This is our Ka. And again, we're setting up the icebox because we have a weak acid ruling the pH. Now this will be the original icebox, not the modified, because we don't have a buffer. All we have is that weak acid in the solution. So let's set up the icebox. This should bring back fond memories of chapter 16 as we were calculating pHs of weak acids or weak bases using iceboxes. So we have 0040 moles of our acid. We had 0 of these. This is how we solved the icebox in chapter 16. And then we know that we have at the equivalence point, as we get to equilibrium, we're going to subtract on the left side and add on the right side. This is where we have to use x's. So we have 0040 minus x. Here we have x, and here we have x. So then our Ka, which was 5.56 times 10 to the negative 10, equals x squared over 0.0040 minus x. Remember, there's a shortcut to the icebox. The shortcut said that we can ignore this x. And then this allows us to solve for x a little easier. And then we just multiplied over to this side, and x ended up being the square root of 5.56 times 10 to the negative 10 multiplied by 0.0040. This is back to chapter 16, solving iceboxes of weak acids and weak bases. So if you forgot how to do this, then refer back to those videos. So we have 5.56 times 10 to the negative 10 multiplied by 0.0040, and then square root that. So we end up with 1.49 times 10 to the negative 6. This is our moles of H plus. And remember, this is what we're solving for, because in the end we're going for the pH. We were asked for the pH at this equivalence point. So now if we want a negative log of this, it has to be in molarity. Because we solve for moles, we need to put it in molarity. In order to put it into molarity, we'll have to find out how many liters was added through the titration. If you look back at the original problem, it says that we're adding 40 milliliters of our base, which means we're going to have to find out how much of the acid had to be used up for that titration. Now, because our molarities are the same, this is actually going to be quite easy. We're going to have exactly 40 milliliters of our acid. Now, if the molarities were not the same, what you'd have to do is find the moles of each, and then find out how many liters you would need of the acid. This is like we did in example 6 or 5. Refer back to example, I think it was example 6, if I'm not mistaken. Yes, example 6. So look back to example 6. But in this case, we have total 80 milliliters. So milliliters total was 80. Again, you may have to calculate a different value if your molarities of the acid and the base are not the same. So this gives us actually 0.080 liters. So we can now get our molarity of our H plus, which is 1.49 times 10 to the negative 6 moles over 0.080 liters. And this molarity then comes out to be try that again. Do 1.49. We should get 1.86 times 10 to the negative 5. pH, this is molarity of H plus. So the pH is negative log of that. So take the negative log of 1.86 times 10 to the negative 5 on your calculator. And that gets us 4.73 for our pH. So notice this whole problem focused on finding the pH at the equivalence point for a weak base titration. And it was quite an adventure. Notice we did a good hefty amount of calculations in order to determine the pH at the equivalence point of a weak base. And notice it's acidic, the pH is acidic, which is in keeping with the fact that we neutralize a weak base and produces a conjugate acid. That conjugate acid, which in this case was NH4+, rules the pH and makes it acidic. So this concludes lesson 4 of chapter 17.